Hello, algebra students. Welcome back to our latest video lesson. Today we're going to understand, explain, and apply what is called Newton's formula to real-world situations. Yesterday, you explored inside of Desmos on what some of those applications of real-world situations might be. An object falling from a building, a cannon, shooting a cannonball, things like that. And so we've got to understand this first part known as Newton's formula. So I am working out of a new packet here. I linked to that today inside a classroom, and we're starting on page 1. Projectiles in Newton's formula. So these are some equations and some information that I've been told you've worked with in science. The force due to gravity, or the force of gravity, which is also called acceleration at 32 feet per second squared, or 9.8 meters per second squared, depending on your unit of measurement. We have an initial upward velocity, meaning how fast is it going up, known as v sub 0. And an initial height, which we call h sub 0. So those are some general terms. You don't need to memorize those. You don't need to necessarily even have all of that written down, because in general, we're going to be looking at the height, how high is an object or a projectile over a certain amount of time. And when we look at them, we do need to look at them in two different aspects. One, if we're using feet as our measurement versus meters. They're almost identical, except for the part in front of t squared, where t stands for time. Feet is going to be negative 16t squared plus v sub 0, which is our initial velocity, times t, plus h sub 0, which is our height. And then we have the meters, which just replaces negative 16 with the negative 4.9. T squared plus v sub 0. I would make sure you have those two equations written down, and you know which one represents which element. I hope that makes sense. Right? Meters and feet. Very important. Okay. Now, notice both of these are quadratic formulas. These are formulas, but they're in the form of y equals ax squared plus bx plus c, where in this case t is the actual value of x. Okay, and we can use some of our properties that we learned and did with quadratics and graphing in our last chapter and test. Now, you did some of this already yesterday in that Desmos without even knowing it, ironically. You had that object falling from a building, it looks like, where it took 6 seconds for the object to fall all the way down and hit the ground. So a couple of questions that I have for you. According to that graph, what was the initial height of that object? How high did it start? Well, the height here was 500 feet. It was indeed 500 feet. What is the initial velocity? So here's the formula that it gave us. Negative 16t squared minus 500. So if I go back a page for a moment, notice initial velocity is going to be right in front of the t, not the t squared. So in this problem, we don't have an initial velocity. Its initial velocity was 0 feet per second. Why is that the case? Well, in this case, the ball was being dropped from the building. It wasn't being shot up into the air. It's as if somebody stood at the top of the building, put their arm out, and dropped whatever object. And that's a key observation and note. You need to know this. Whenever you see that an object is dropped, the key word being dropped, our initial velocity will always be 0. That is key to understanding Newton's formula. If it's dropped, the initial velocity is 0, and that's what we can plug in, why we don't have a middle term. Now, the second one you worked on was this cannon, and it was modeled by this equation. Negative 16t squared plus 120 times t plus 10. Okay, so what is the initial height of the cannon? Where was it being shot from? Well, if I try and match up the equation for Newton's formula with here, the initial height was 10. That h sub 0 is the constant, has no variable. And what was the initial velocity of the cannon? 120, because it's right in front of that t. So 120 feet per second. So in 1 second, it travels 120 feet up into the air, and it's going to keep going. And again, I'm just pulling the information out from the equation that they used to model it based upon the formula, matching those up. I know it's feet because we're using negative 16. The last one that you used was the height of a ball after kicking it, right? Like if somebody's kicking a football off of a tee to start a game off, or even a soccer ball maybe. And they give us this formula, negative 4.9 t squared plus 12 t, which is meters. What is the initial height of this football? Where did it start? So if I try and match up this equation with this formula, notice I don't have anything out here for my height. They don't have that. So the initial height was 0, meaning it was kind of kicked off the ground, right? When an object is on the ground, the initial height is 0. The initial height will be 0, and that's in a sense what you do plug into the equation. So again, we can use these different formulas to help us identify certain elements of an equation. Let's take a look at some examples. I'm still in your packet. I believe I'm on page 1, maybe the top of page 2. This first example talks about a ball being thrown from an initial height of 10 with an initial velocity of 64 feet per second. Write an equation describing the height in feet of the ball after t seconds. So try and pick from the Edpuzzle multiple choice which equation we should use. The first element to decide is, are we going to use negative 16 t squared or negative 4.9 t squared? Remember, this is for feet and this is for meters, and they're telling us that it's in feet. So h of t, the height after some certain amount of time, equals negative 16 t squared plus v sub 0. That's my initial velocity. So that's 64t plus our initial height, our h sub 0, which was 10. So I'm plugging that into the feet problem, just replacing v sub 0 and replacing h sub 0. Everything else stays. Now they'd like to know, how high is the ball after 3 seconds? Well, that means my time, or my t values, are 3. So I need to evaluate by plugging in 3 into that entire equation. And then we're going to calculate that to see what value we get, and that would tell us our height. 3 squared, that would be 9. Excuse me. And then 9 times negative 16 is negative 96, plus 64 times 3 is 192, plus 10, and we're going to add all of those together to get a grand total of 106, or 106 feet. So after 3 seconds, this ball would be 106 feet above the ground. Okay, above the ground. Now the last question asks, what is the maximum height of the ball? And if you remember from what we just did, the maximum height occurs at the vertex of this parabola, which means we have to go to Desmos. All right. That's why we graphed and talked a lot about looking at information here on Desmos. The equation we had was y equals negative 16. Instead of t, we have to use x, though, because Desmos does not like t. So I'm just going to replace the t with x. and grab the rest of the equation, and you can see that it doesn't quite fit. So I'm going to have to maybe zoom out. Oh boy, look at, well, we knew that it went over 100 feet. Come on. The maximum height would be 74. All right, the maximum height would be 74. So I'm going to go over here and type in 74. Now, for some reason, that doesn't make sense in my mind because we calculated 3 seconds to be, what, 106 feet. So maybe we did something wrong. And I certainly did. I multiplied 3 squared times 16 wrong. So that really should have been negative 144, which makes this value slightly different at 58 feet. So you can see how you can use the graph to help you figure out that maximum height and then realize that we maybe miscalculated something previously. So the max height came from the vertex of the graph. There's x equals 2 right through there. So you'll want to be able to punch that in to figure out some of those characteristics. Our second example comes from number 2. A ball is dropped from an initial height of 90 meters. 90 meters. What is the initial upward velocity of the ball? How fast is it going upward? Notice there's a key word that it was dropped. So it is 0, in this case, meters per second. 90 meters, right? Dropped means we're just letting it fall. We're not going upward at all. The initial height is 90 meters. And now we should be able to plug that into the formula. Negative 4.9 t squared plus, we would have 0 times t, but 0 times anything is 0, so I don't have to write anything in there. So then I go to plus the original height, which was 90. The height of any object after t seconds is going to equal negative 4.9 t squared plus 90. And now we've got to be able to answer some questions. After how many seconds will the ball hit the ground? What is the maximum height? After how many seconds is the ball 40 meters above the ground? And so on. So let's go see these two by graphing on Desmos. Negative 4, y equals negative 4.9 x to the second plus 90. Because it was 90, because it started at 90 meters. And I'm going to go back up to this wrench, and I'm going to change my windows. The x-axis, I'm going to set equal to, let's go negative 2, all the way up to, let's just look at up to 10 seconds. And then my y-axis, let's go from negative 2 all the way up to, it looks like we might have to go to like 120 maybe. So by changing the window, you can see what's happening. Now, what is the maximum height the ball reaches? Well, if a ball is being dropped off of a building and it's falling, the maximum height was where it started. So that would have been 90 feet. How long until it hits the ground? Well, if I'm looking at the graph, the ball started way up here at 90 feet, and eventually it hits the ground right there, where y is 0. The height was 0, or 4.3 seconds. 4.3 seconds. And the last question is, after how many seconds will the ball be 40 meters? I want to know where it is 40. Now, I could try and graph and pick that up exactly, but if I do that, I'm slightly off. So I want to know where does y equal 40? That height equals 40. It'll give me a point of intersection. 40 for a height at 3.2 seconds. At 3.2 seconds, because the height on our graph was represented by the y-axis. I could plot that second line on there to see where do they do indeed intersect. So hopefully you see how all of this is tying together. These two formulas are the most important ones that you'll need for this Newton's formula, and knowing what to plug in where, paying attention if something is dropped. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe